Hello everyone, this is Tim Benjamin and we are going to present geometric transformations. Part 1, Technical Details. First, let's define geometric transformations. The concept of operating of geometric transformations is an operation that is applied to the geometric description of an object to change its position, orientation, or size. Uses of geometric transformation. We can find uses for viewing routines that convert a world coordinate scene description to a display for an output device, or in computer-aided design and computer animation. Also, we will find uses to describe how objects might move around in a scene during an animation sequence, or simply to view them from another angle. The first transformation we are going to explain is translations. We're going to start with 2D transformations and later we're going to work with 3D transformations. A translation on a single coordinate point is performed by adding offsets to its coordinates. The translation distance pair, Tx, Ty, is called a translation vector or shift vector. We can see this representation in the graph on the left side. P is the original point and P prime is the translated point. T in this case is representing the translation vector. The blue arrows are representing the components of this vector. The equation to generate a translated point is defined by x prime equals to original x plus the translation coordinate in x, and similarly y prime is going to be the original y plus the translation in the y-axis. In the case of a polygon, it is translated by adding a translation vector to the coordinate position of each vertex and then regenerating the polygon using the new set of vertex coordinates. We can observe this with the red arrows in the graph to the left. A translation is a rigid body transformation. This means that the object or polygon, the triangle in this case, is not deformed after the transformation or during the transformation. The matrix notation. It is possible to express the previous equation as a single matrix, but by using column vectors to represent coordinate positions and the translation vector. As we can observe here, if we define P, the original point, as a column vector xy, and P prime as a column vector x prime y prime, and the translation as Tx, Ty, then we can rewrite the two-dimensional equation in the matrix form P prime equals P plus T. The following is the code of a function to perform the translation transformation in 2 dimensions. The function receives a set of vertex, a value for number of vertex, and the translation in x and the translation factor in y. The logic of this operation iterates over each vertex and generates a new vertex or a new set of vertex by adding the translation shift to each of their coordinates. After having the new set of coordinates, the polygon is regenerated. Rotation. To perform a rotation over an object, a rotation axis and a rotation angle must be defined. All the points of the object are then transformed to new positions by rotating the points through the specific angle about the rotation axis. In this case, the rotation axis is this dot, and the theta is going to be the angle to be rotated. this triangle is going to rotate each of its vertex. For example, this vertex is going to rotate a theta angle, this vertex is going to rotate a theta angle, and this vertex is going to rotate a theta angle. And then after those vertex are rotated, then the new triangle or the rotated triangle is going to be redrawn. In the case of a 2D rotation, the rotation axis is perpendicular to the xy plane. In this case, the parameters are theta, the rotation angle, and a rotation point instead of a rotation axis, represented by xr, yr. The rotation of a point when the pivot point is at the coordinate origin can be represented by the following variables. R is the distance of the point to the origin, the original point. Phi is the original angular position. We can see this here in the picture. This is the original P. This is the original angular position of this point P. And theta is going to be the rotation angle, the desired rotation. If we perform this rotation, then we can observe that the new P or P prime coordinates are going to be defined by R, that's the distance to the origin, multiplied by the cosine of the sum of these two angles, phi and theta. We can observe that here. Similarly, we can apply for y using the sin function. And if we apply trigonometric identities, we can obtain this formula. We can observe that r cosine of theta, of phi, is equal to x. So we can replace x here, and we can replace in the similar way y in this portion of the equation. So we are going to end up with this set of equations that depends only on the original point coordinates and the desired angle. The matrix notation. If we have P defined as xy and P prime defined as x prime, y prime, and if we define the rotation matrix as we can see here in the slide, then we can rewrite the rotation equation in the form P prime equals R times P. If the 2D rotation is with respect to an arbitrary point, then it is possible to generalize the previous equation as we can see here. So in this case, x, that originally was this distance, now since this is not the origin, then we need to define which is this distance. This is x minus xr, that is the rotation point. Similarly, y, this will be the original y minus the rotation point in y. The rotations are rigid body transformations. Again, in this case, the polygon vertex, if we are going to rotate a polygon, every vertex is going to be rotated, and then the polygon is regenerated. Defining points of a curve, in the case of a curve, we're going to rotate the defining point and redraw the curve. And in the case of a circle, the center is moved through an arc, and then we are going to redraw the circle. Again, this is a function using OpenGL that rotate a polygon. We receive a set of vertex, a number of vertex, a pivot point, and a desired angle to be rotated. We go over each of the vertex and rotate them. And with a new set of vertex, we're going to regenerate the polygon. Transformation scaling. That's the third transformation in 2D. A simple 2D scaling transformation is performed by multiplying object's position xy by a scaling factor sx and xy. The function that describes this transformation is x prime equals the original x times fx and y prime equals to the original y times sy. The 2D scaling transformation can be written in the matrix form x prime y prime equals to the matrix, the transformation matrix for scaling, times the column vector for P. So we will end up with P prime equals S times P. Any positive number can be assigned to scaling factors. When the scaling factors are equal, a uniform scaling is generated. When the scaling factors are not equal, a differential scaling is produced. In some cases, some systems accept negative scaling factors, which this in turn will resize and reflect the object. The example figure to the left will translate scale this figure A into this figure B. The scaling factors are x equals 2 and sy equals 1. These two in the scaling factor in x, we can see that the value for x is multiplied by 2, while the value for the y coordinates are kept the same because the scaling factor is 1. When objects transformed with the scaling matrix equation are both scaled and repositioned. Scaling factor with values less than 1 will move the object closer to the origin coordinate, and scaling factors with value greater than 1 will move the coordinate position farther from origin. In the example to the left, we can see that this line is transformed, is scaled by 0.5. This is a uniform transformation. So it will be closer to the x, will be reduced closer to the origin, and in y also will be close to the origin, this point. And at the same time, the line is scaled by a half. It is possible to control the location of a scaled object by choosing a position called the fixed point. So we are going to redefine the previous equations as x prime minus xf, that is the fixed point, equals to x minus xf times sx. Similarly for y prime minus yf will be equal to y minus yf, the fixed point, in y times sy. This will be changes or reformulated as we can see here, and we can notice that these adding factors to the right are going to be constant because the xf and yf are constant values for all of the vertex, and 1 minus sx and 1 minus sy are also constant because x and sy are the scaling factors that are the same for all of the vertices. This is the scaling function for a polygon. We receive again a set of vertex, a number of vertex, a fixed point, a scaling factor in x, and a scaling factor in y. We're going to iterate over each vertex, and we are going to scale it by the factor and according to the fixed point. And with the new set of vertex, we're going to regenerate the polygon. Homogeneous coordinates. Sometimes, or most of the time, animations might require that an object to be translated and rotated at each increment of the motion. This can be represented as P prime, that's the new state of the object, will be M1, the matrix 1, times P, or P is the original point, plus M2. M1 here is a 2 by 2 matrix for rotation and scaling. M2 is going to be a column vector for translation. Matrix representation can be reformulated so that transformation sequence can be processed efficiently. A more efficient approach is to combine transformation. We're going to talk about later about combined transformation. For now, let's focus on the representation. Homogeneous coordinate. Multiplicative and translational terms for a two-dimensional geometric transformation can be combined into a single matrix if we expand the representation to a 3 by 2 matrix. The third column can be used then for the translation terms. But we need to expand the matrix representation of a coordinate position xy to xh, yh, and h. This is called a homogeneous coordinate. In this case, x is going to be equals to xh divided by h, and y is going to be jh divided by h. Therefore, a 2D homogeneous coordinate could be written as h times x, h times y, and h. We define h times x is equal to xh, as we can see here. Normally, h is selected as a non-zero value and normally equal to 1 most of the time. The term homogeneous coordinate is used in mathematics to refer to the effect of this representation on Cartesian equations. When a Cartesian point xy is converted to a homogeneous representation, the equation containing x and y, such as fx equals 0, becomes homogeneous equations in the three parameters xh, yh, and h. Expressing positions in homogeneous coordinates allow us to represent all geometric transformation equations as matrix multiplication, which is the standard method used in graphic systems. So here are the translation matrix for using homogeneous coordinates. We can represent the equation for a two-dimensional translation for a coordinate position, as we can see here. So basically, the third column will have the translation shift in x and in y. And in the bottom, we have an example for this. We suggest you to pause the video and pay attention to the multiplication of the numbers. In the case of a rotation matrix, the two-dimensional rotation transformation equation about the coordinate origin can be expressed in the matrix form. We can observe that these first two columns and first two rows correspond to the rotation matrix, the original rotation matrix. In this case, the values or the column for a shift or for a translation is equal to 0, except for the one in this column. Okay. Again, in the bottom part, we have an example that you can check for a small test, a simple test. The scaling matrix using homogeneous coordinate can be represented as follows. We're going to put the scaling factor for x in the first corner of the matrix. In the position 0, 0, in the position 1 and 1, we're going to use sy, the scaling factor for y, and then a 1 in the last corner of the matrix. Again, at the bottom, we have an example, so we can check on numbers. This inverse transformations. Inverse transformations are also called opposite transformations. An inverse geometric transformation performs the opposite operation performed by the original transformation. An inverse transformation is applied in a similar way as the original transformation. The multiplication of any 2D transformation matrix at its inverse will produce the identity matrix. How do we obtain the inverse transformation matrix? In the case of a translation, The inverse translation matrix is obtained by negating the translation distances. For example, if this is the original transformation, the inverse transformation will be generated by minus tx minus ty in the place of tx and ty. For rotation, an inverse rotation is accomplished by replacing the rotation angle by its negative. So for example, if we have cosine of theta, we're going to replace it by cosine of minus theta, but it's the same. In the case of sin of minus sin of theta, we know that the sine of minus theta is going to be minus sine of theta. Then we obtain this new matrix as the rotation matrix for inverse transformation. And finally, the inverse transformation for scaling, we're going to generate this matrix by replacing the scaling parameters with their reciprocals. So we replace fsx by 1 over sx and sy by 1 over sy. This is the inverse transformation for scaling. So this is all. Now my classmate, teammate, Xiao Han is going to present the next part. Thank you.
Part 2. Presenter is Xiao Han. I have 3 topics. First, composite 2D transformation. Second, rotation scaling with respect to an arbitrary point. The final one, efficiency of homogeneous coordinates. Let's first talk about what is composite 2D transformation. Composite 2D transformations is the process of combining several transformations in succession on any object to form complex transformations. For example, if we apply two transformations M1 and M2 consecutively to a point P, the resulting point P dot would be calculated as P dot is equal to M2 times M1 times P, where M2 and M1 can be times the M1 can be represented by M. Consider transformations may not be commutative. The order for matrix matter and should be preserved. Next is about our first topic, two successive composite 2D transformations. So for example, we have two translations. We apply two translations, or we apply two rotations, or two scaling to an object. Firstly, the composite translation. If we translate a shape with two successive translation vectors, tx1, ty1, and tx2, ty2, it is equal to a single translation of tx1 plus tx2, ty1 plus ty2. This additive property can be demonstrated by the following equations and matrix, where the composite 2D transformation with two translations can be represented by the following matrix. Next, we talk about the composite rotation. If we rotate a shape with two successive rotation angles, theta and alpha, with respect to the origin, it is equal to rotating the shape once by an angle theta plus alpha with respect to the origin. Similarly, this additive property can be demonstrated by the following composite transformation matrix. Next is about the composite scaling. If we scale a shape with two successive rotation angles, sx1, sy1, and sx2, sy2, with respect to the origin, it is equal to a single scaling of xx1 times sx2, sy1 times sy2 with respect to the origin. This multiplicative property can be demonstrated by the following matrix, transformation matrix, composite transformation matrix. Here we come to the second topic, 2D transformation with respect to an arbitrary point. So before this topic, we only talk about the transformations with respect to the origin of the coordinates origin. First, we talk about the rotation with respect to an arbitrary point. Rotation repositions all points in an object along a circular path in a plane centered at the pivot point. Assume we rotate an object by an angle, the theta. The new coordinates of the object after rotation depend on both coordinate x and y before the rotation. Usually the rotation with respect to an arbitrary point consists of the following three steps. First, we translate the shape to the origin. Next, we rotate it about the given angle. And then we translate it back to its original position. So here we have an example. From the figure on the right, we rotated the triangle ABP to triangle ABP dot by an angle theta. In general, rotation equation about origin is given as x dot is equal to r times cosine phi plus theta. Y dot is equal to r times phi plus theta. Considering about an arbitrary point from triangle ABP all around in the coordinates, we have the following equations: r times cosine theta is equal to x times x minus xr. R sine theta is equal to y minus yr. The rotated point is given as the following equations: s dot and y dot. So considering rotation using homogeneous coordinates about a fixed point like SR and YR, by decomposing the following matrix, we have the following. We have the matrix on the bottom consists of three matrices. It's pretty much equal to the three steps mentioned earlier. So we first translate it to the original origin. Then we rotate it about the angle, and next we translate it back to its original shape. Next we talk about the scaling with respect to an arbitrary point. This controls the location of a scaled object by choosing the location of a fixed point, with respect to where the scaling is performed. It also consists of three steps. First, we must translate the object so that to appear coincident with the origin. Next, we scale the object with respect to scaling factor as x as y. And finally, we translate it back to its original shape position. In matrix form, we have the following equations: s dot is equal to s times x times sx plus x for f times y minus sx. Y dot is equal to y sy plus yf times y minus sy, and also the following matrix equation. If we scaling using homogeneous coordinates about a fixed point, we have the following equations. By decomposing the second matrix, the most complex matrix, we have the three matrix on the bottom. It's also the same as what we have discussed earlier, those three steps. We first translate it to the origin. Then we do the scaling, and finally we translate it back to its original position. Here is the math where the composite 2D transformations. If we want to apply more than two transformations, say T1, T2, and T3 in series consecutively, it can be done in two ways. First, we can calculate P1 is equal to T1 times P, and then we can calculate P2, which is equal to T2 times P1. And eventually we can calculate the final transformation P3, which is equal to T3 times P2. And on the other hand, we can calculate it. We can first calculate the T, the overall composite transformation T, which is equal to T1 times T2 times T3. And then we can do the final transformation by calculating P3, which is equal to T times P. If we want to apply a transformation M1 to a point P, xy first, and then transform using M2 and M3 successively, we have the following equations. Note that matrix multiplication is associative. So next question is that is the order of transformation relevant? So basically, transformations may or may not be commutative. So here it shows the commutative properties. We also have some commutative cases, like to translation consecutively, to scaling consecutively, to rotations successively, and we first perform uniform scaling and then we perform rotation. Here is my final topic, computational efficiency. Homogeneous coordinates translation is addition, while scaling and rotation are multiplication of matrix. So it will be better if we can express all three transformations by using a general matrix multiplicative form. So here it comes to the advantage of homogeneous coordinates and homogeneous transformations. First, we represent all transformations as matrix multiplication. And next, we capture composite transformation convenient. And that's all my part. I'm gonna transfer it to my partner team. Next team.
So the next part of geometric transformations covers the topics rigid motions, reflection and shearing, raster methods, transformation between coordinate systems. And the first topic is rigid motions. The name or the word itself says rigid means fixed or solid. So the formal definition of a rigid body is a change in coordinate system or the transformation of an object from some point or location to some other point without changing the size or shape of the object. So the rigid motions do not include transformations like scaling and shearing. Scaling itself says that it's resizing an object. So, according to the definition of the rigid motions, scaling does not include since it is resizing the object. Shearing means it reshapes the object or it slants the object's shape. So, it also does not include in rigid motions. So, the only transformations that get included in rigid motions are translation, which is also called as slide, rotation or turn, and reflection, which is also known as flips or the mirror image. So the first one, this is a brief description of all the three transformations that get included in rigid motions: reflection, rotation, and translation. So the first one, translation, is just the sliding. Reflection is the mirror image. Rotation is turning with an angle theta to either of the side with a clockwise direction or the anti-clockwise direction. And the first one, translation. The name itself says that it is just translating. It is not changing the size or shape of the object. It is just moving its location from one coordinate points to the other coordinate points in the system. So it is what mentioned here. It's a push or slide of an object. So it is in this triangle, it's just moved a bit to the right in the same plane, and it stays in the same way as it is. So the example for translation here, I took Super Mario Maker. This is just a game that we all used to play when we were kids. So this is a Super Mario Maker level, and the screenshot in that level where this as a character this as a character called Mario, and these are the sauce and these are the base. These saws can move up and down, and thus Mario can move in any of these directions as shown by these arrows. So, while this character tries to move from here to here, it does not change its shape or its size, and it is not even rotating through some angle or not flipping. So it's just moving from one place to the other. So this kind of moving or this kind of sliding is known as translation. The next one is rotation. Rotation itself sounds similar. It's just a turn through an angle, some clockwise direction or anti-clockwise direction. Here I just took the example of a triangle and the knob. So this triangle is making a turn with 90 degrees clockwise direction, whereas this doorknob is rotating in 180 degrees anti-clockwise direction. Even if this knob is changing its direction or even it's trying to rotate, it is not changing its shape or size. It is being fixed and it is the same as it was. So, and again, the example of Super Mario Maker. Here, the sauce moves up and down as well as it rotates itself while moving up and down. So, these saws come under example of rotation. Then the reflection. Reflection itself says that it is a flip or a mirror image. So here I took this triangle and made a mirror image with respect to the y-axis or the vertical axis. So if I took this point as a major one for flipping the triangle, and if I flip this triangle in this way, it will be in this way. And again, the Super Mario Maker, if we take this example again, so here if we pre-assume that this character is going to die or suck in between the saws and he might die and the game might end, then the Super Mario can change its direction and go backward as it came. So in order to go backward direction, it just flipped its way and then trying to move backwards. So this flipping backwards is example for reflection. These are some of the games that include rigid motions of reflection, rotation, translation, a Pac-Man video game and a ball pole game and a lot money. So here is another matrix representation for 2D transformations. So when we take only translation and rotation, the Ri parameters represents the multiplicative rotation terms, whereas Trx and Try are the translation terms. So when we consider each row or column of this matrix as a vector, then we can see that row vectors or column vectors form an orthogonal set of unit vectors. And next topic is reflections. So as discussed earlier, reflections, it's a mirror image or a flip. If we take a two-dimensional reflection, it just takes 180. It can rotate in any of the directions with any of the theta with any of the angle of rotation. So if we consider the axis of reflection can be in xy plane or perpendicular to the xy plane. So in the case where the reflection axis is a line in the xy plane, the rotation path will be perpendicular to this xy plane, and vice versa, which is if the reflection axis is perpendicular to the xy plane, then the rotation path is in xy plane. So reflections with respect to x-axis. So if we can see, we are trying to reflect this image with respect to x-axis. So here, this we are trying to use this part of the triangle to make a flip. So this x-axis terms does not change, only the y-coordinates gets changed. And we are trying to flip from first quadrant to fourth quadrant. So the y-coordinates becomes negative. So the x has no change in the value of the new x-coordinates, but y has a change in its value and it's becoming negative. Similar is the way reflections with respect to y-axis. If we consider the original position of this triangle, this is making a flip with respect to only this point, and if this makes a flip, only the x coordinates gets changed and not the y coordinates. Y coordinates stay similar. So the x coordinates is the new x coordinates, but the y coordinates remains the similar. So there will be the only change in x coordinates. And then the reflections with respect to this diagonal. This as the diagonal. So reflections from one quadrant to the other, like from first to third or second to fourth or second to third, etc., can be defined as diagonal reflections. So let's consider the first one, reflections from first quadrant to third quadrant. So since this is reflecting with respect to this point and trying to reflect this way. So, if we consider these points, this is the first quadrant, which means both x coordinates and y coordinates are positive. So we are making a flip to the third coordinates. So when we multiply it, here the x and y are the negative terms. So when we multiply, automatically we'll get the negative coordinates for both x and y. Similar is the way when we do a reflection from second to the third, fourth, then we get x coordinates and y coordinates as negative, since x is negative in second coordinate and y is negative in fourth quadrant. When we multiply both of these, we'll get negative for both x and y new coordinates. Similar is the way for reflection with second and third quadrant. The next one, reflections with respective to arbitrary axis. So here, this is the original position where this arbitrary axis is not aligned with the origin. So the first step is we are translating this line to origin. So this will be the next step. So once we translate the line to the origin, then we are making a rotation with about minus theta degrees in order to meet this to the origin. So once the rotation is done, this will be the position. So here it is. Then we are trying to reflect this matrix. So we are trying to reflect from first quadrant to fourth quadrant. And then the image will be in this way. So once it gets reflected, we are again rotating this back to theta degrees in order to obtain this axis, and then we are again translating this back to the same length in order to get the original arbitrary axis. This is how we do reflection with respect to the arbitrary axis. The final matrix would be translation multiplied with all the terms: translation, rotation, reflection, then the inverse of this rotation, and then the inverse of translation. And this is some example which I took for reflections. Here it is getting reflected in the bottom way in either of the directions. The next topic is shearing. So the transformation that slants the shape of the object is called shear transformation. So a transformation in which all the points along a given line remain fixed while the other points shifted parallel to the L. That can be either x or y axis um, by a distance proportional to their perpendicular distance from L. So this is what called as the shearing. It can occur in both x-axis and y-axis. However, in both the cases, only one coordinate point changes, and its coordinate points and the other values will be the same. This shearing is also termed as skewing. So here is the graphical representation of shearing with respect to y-axis. So here shearing with respect to y-axis. If this is the original object, then we are trying to shear this with respect to y-axis. If we can observe, only the coordinate points of y-axis will be changed and x will have no change in its values. If we can see, the points of x will be the same, whereas the y is changing its distance from the original object. So the matrix representation would be YSH into so the final matrix representation would be the new coordinates of y would be y plus sy sh of y into x, and the x coordinate as discussed would be the same. And shearing with respect to x-axis. So here the shearing points of new x coordinates only gets changed and the y remains the same. So the matrix representation would be the new points of x coordinates is x plus shearing of x into y, and the y points remains the same. Next topic is raster methods. So the raster methods also called as bitmap graphics, since it is a type of digital image that uses these tiny rectangular pixels or picture elements arranged in grid formation to represent this image. Raster is technically characterized by width and height of the image pixels and by the number of bits per pixel or color depth, which determines the number of colors it can represent. There is one more technique called vector representation or the vector graphics, which takes a clear pixel of colors, whereas this raster methods take this rectangular pieces, the grid formation of the image. The raster systems store picture information such as color patterns in this frame buffer. So if we can observe, it is picking this part of the color and making a frame buff of color patterns or the shades of the same color with different shades. Some simple object transformations can be carried out rapidly by manipulating the array of pixel values. Few arithmetic operations are performed on this array so that the pixel transformations are particularly efficient. So the functions that we operate on or manipulate on these rectangular pixel arrays are called raster operations. And when we move a block of pixel values from one position to the another is termed as block transfer. So if we see this, it is rotation with arbitrary degree. So here it is the destination pixel array. So this is the destination pixel array. And this is the destination pixel area, and this is rotated pixel array. So when we consider the destination pixel area, it is mapped onto this rotated pixel array. And then the amount of overlap with this rotated pixel array is calculated. A color for a destination pixel can then be computed by averaging the colors of the overlapped source pixels weighted by their percentage of area overlap. This is rotation with arbitrary degree and then scaling with arbitrary factor. So scaling is itself says it's resizing. This is a scaled array. This is the destination pixel array. So pixel arrays in the original block are scaled using values for Sx and Sy, then mapped onto a set of destination pixels. The color of each destination pixel is then assigned according to its area of overlap with the scaled pixel arrays. And then translation. So this is a two-dimensional translation implemented as a block transfer of a refresh buffer area. So we are trying to translate this refresh buffer area from here to here. All the bit settings in the rectangular area are copied onto the block into the another part of frame buffer. So if we want to erase this part of the frame buffer, then we can assign background color to these pixels within this block, so that it will be same as the background color. So we can assume that it is erased. And then rotation. So as discussed, this pixel, if we consider this pixel array, if we made a 90-degree clockwise rotation, then this pixel array becomes this array. If we again apply 180 degrees rotation clockwise rotation on this, then it becomes this pixel matrix. So if we consider this again, this example here, it is if we consider this as the original object, if we apply translation to this original object, it becomes this. If we apply rotations on this object again, then it becomes this. So this is a translated and rotated object. The next one is the transformation between coordinate systems. So so the 2D coordinate system deals with both x and y axis, horizontal and vertical. These coordinates mapping helps in visual depiction. The coordinate transformation from one reference frame to the other reference frame is crucial, and various computer graphic applications. We say here, see, this is an Excel with coordinate points as 1 and 1. This is XZ with coordinate points, and this is L. So the steps for composite mapping is, first we are using translate origin of model frame to origin of world frame. New origin at this point would be T new is this matrix. And then we are constructing a rotation matrix that rotates this model frame to the world frame, and this would be the new rotation matrix. And then we are trying to construct the matrix M by multiplying the rotation matrix obtained here and the translation matrix obtained in the first step. And here this would be the final matrix. So this common matrix for rotation and translation, when we consider the geometric principles, then it would be in cos theta, cosines, and sine values. So here, so the next part would be continued by my friend. Thank you.
Hello guys, so let's continue the presentation. My name is Subhash Burati, and the topics we are going to discuss now are 3D transformations in translation, rotation, scaling, reflection, shear, and transformation between 3D coordinate systems. So starting with 3D transformations, what does 3D transformation mean? The process of performing transformations in a 3D plane on all the x, y, z. So on the x, y, and z axis is called as 3D transformation. So on the 3 axis, if we perform a transformation, then it is called as 3D transformation. So what does this transformation help us in doing? So this transformation helps us in change the position, size, and shape of the object. So basically the transformation in computer graphics can be divided into 5 types. Those are translation, rotation, scaling, reflection, and shear. So moving the first one, translations. So 3D translation means moving one object from one position to another position over a straight line. So for example, let us take a point O. It is an X all, Y all, Z all position. So it's moving from one plane to another plane over a straight line. So this is called as a 3D translation. Cause if it moves on a single line, straight line, then it's called a translation. But if it's happening in a three-dimensional, so that's a 3D translation. So let us get a small example. So let us take let us check that with let x object be the x all, y all, and z all, and then the p1 is be x new, y new, and z new, and the translation vector be tx, ty, and tz. So given a translation vector tx, ty, tz, tx defines the distance between x old coordinate which has to be moved, and ty defines the y all, and tz defines the z all. So the point it's from the O to O dash. So the distance moved by the x point, y point, and z point are noted as tx, ty, and tz. So moving on next, x new can be found using the adding the translation done over the x-axis, y-axis, and z-axis. So for x new, we are going to add the translation of x-axis to the x all point, and same goes with the ty. We add with the y all, and tz we add with the z all. So that gives us the new x point, y point, and z point where the new object has been moved to a different new position from its old position, and that is called an 3D translation. And this formula can also be noted in a matrix form, that is x new, y new, z new is equal to 1 over tx and o1 over ty and o1 tz, and o1 is being cross multiplied with x all, y all, z all, and so for this formula, so we're going to find x new equal to, so 1 into x all, so it's the x all, and 0 into y all is 0, 0 into z all is 0, and tx into 1 it's tx, so plus tx. So same for the y new, it's 0 tx, or it goes y all plus ty, and for the z new it goes all the 0 0 and 1 with the z all plus tz. So you're going to find the new coordinates using that. So and next, homogeneous coordinate represent. What does an homogeneous coordinate represent mean? So homogeneous coordinate means we are adding a fourth vector. Let us fourth dimension to be more precise. Let us say name it as a w. So let the fourth vector be w. So the reason why we are adding this homogeneous coordinate is it helps us in developing a 4x4 generalized matrix form, and this using this we can find an absolute of multiple points. So multiple infinite points can be declared using this 4x4 transformation. And for example, let us say homogeneous coordinate be x, y, z, and w must not be equal to 0, because if it's 0 it becomes a null point and there's no value for it. So that's the reason it's not must be 0. And we are going to represent a three-dimensional vertex. If it's in a homogeneous coordinate, it's the fourth vector w is going to divide all the x, y, z, so which results in the x, y, z point. And all homogeneous coordinates in 3D levels give rise to a 4D position vector. And using this homogeneous coordinate, we can find infinite points of x, y, z. And next, move into 3D rotation. So 3D rotation means rotating one object from one position to a different position with respect to an angle over a three-dimensional plane. Then it's called a 3D rotation. So we have three types of 3D rotations, and the x-axis rotation, y-axis rotation, and z-axis. In case of x-axis rotation, the x-axis is fixed, and let us take a small example for that. And as usual, like x or object o, x all, y all, and z all, and rotation angle b theta, and new coordinates of the direction x, y new, and z new. And we're going to perform the first one is x-axis rotation. So x-axis rotation means the axis at the x doesn't change. The y and z are the values, the points in the object are going to be changed. So x all remains the same as x new, and y all becomes the formula x cos theta minus z all into x sin theta. For the same new z new is called y all into sine theta plus z all into cos theta. So this can be a three rotation matrix which is defined in this method. And for the same y axis, the rotation happens at the y axis, so y doesn't change, and we can get the x new and z new values from this. And next, going for z axis, the z axis doesn't change, so we get the x new and y new values. And next, moving on to the three rotations for an arbitrary axis. So what does this mean? So three rotation on an arbitrary axis means, let us assume that this rotation axis defined by 2 points. So firstly, we need to translate the object contained from one position to another position. For example, let us look about this drawing, and where the initial pointer is the object is in the position p1 and p2. So we are making sure that one of the point passes through the origin, so where we can perform an arbitrary axis rotation. So we are translating it from an initial position to one of the point passing through the origin. So, and step 2, we are going to rotate the p2, so that we are rotating on the z-axis, so it lies on one of the plane. So in order to perform the rotation, and after it going through an axis, we are performing the rotation over z-axis here. So then it gets rotated, and we are bringing back it to the making sure where the position where we started the rotation before. And and one point is passing through the origin, and now we are going to bring it back to its original position using the transfer option. So performing this, we had done a three rotation over an arbitrary axis. And next, quaternion methods. So what does a quaternion method represent? It is generally present by four elements, where q equal to qo plus I of q1 plus j of q2 plus k of q3. So where q0, q1, q2 and q3 are real numbers, and I, j and k are imaginary unit vectors. The qo term is referred to as a real component, and the three other units are imaginary, that are I, j and k. So let the imaginary be implied, then we will left with only four coefficients which are used to specify a quaternion, and it's q equal to q0, q1, q2 and q3. So rotation quaternions is a mechanism of representing rotation in 3 dimensions, and can be used as an alternative to rotation of matters in 3 applications. So we can rotate a point x, y, z with a quaternion q using 3 steps. So step 1, convert the point to be rotated into a quaternion by sending the point's coordinates as the quaternion's imaginary components, and setting the quaternion's real component as 0. If x, y, z is a point to be rotated, then it's converted the coordinate as follows. So p, p0, p1, p2, p3, where x, y, z are p1, p2, p3, and p0 is 0. So step 2, you are going to perform the rotation. So that implies these are two possible rotations. One is an active rotation, another one is a passive rotation, where p contains the point to be rotated and q is the rotation coordinate. So after the rotation, we get an inverse, which is for q, and its q dash is the inverse for it, and p dash the coordinates of the rotated point. So what does an active rotation, passive rotation mean? Active rotation is when the point is rotated with respect to the coordinate system, then it is called as an active rotation. Then if the coordinate system is rotated with respect to a point, which is vice versa, then it's called a passive rotation. And finally, we are going to extract the rotated coordinates from p dash. So initially p0 is 0 and stays 0, and p, which has been quaternion rotated, it becomes p dash, and x becomes an x dash, y becomes a y dash, and z becomes a dash dash. So the 3D coordinates of the rotated point x, y dash are therefore just imaginary components of p dash. So next, moving on to 3D scaling. So what does 3D scaling mean? 3D scaling is a process of modifying or alternating the size of the objects. So scaling is used to reduce or increase or the size of the object. So scaling factor determines whether the object is to be increased or reduced. If scaling factor is greater than 1, then the object size is increased. If scaling factor is less than 1, the object size is decreased. So the steps to perform scaling are there's an object at the initial position, which is also can be called as an original position, and we are going to translate it, making sure that one of the axis of the object passes through the origin and one of the axis, and then we are going to perform a scaling option, and then we are moving it back to its original position. So in previous case, we have increased the size of the object. So for example, let us take initial coordinates x equals 0, o, y, z, and scaling factor of x be s of x, and scaling factor of y be sy, and scaling factor of z be xz. So new coordinates are scaling of x new, y new, and z. So x new can be defined into x all into x of x, which is the scaling for x axis, and y new can be defined out by using y all into x of y, which is scaling for y axis, and z new is z all into x of z, which is scaling of z axis. So moving to the next topic, is reflections. So what is a reflection? And an object is rotated by 180 degrees, and which the result is a mirror image of itself. Then it's called a reflection. So there are three possible reflections, and they are the reflection related to xy plane, reflection related to yz plane, and reflection related to z plane. So consider point object to 0. O has to be reflected to the plane. Let initial coordinates are the x all, y all, and 0. New coordinates are reflected O object reflection be x new, y new, and z. So reflection is xy plane. So it being an xy plane, so the x and y doesn't change, so x old becomes x new and y old becomes y new, but the z is on a positive axis, so it moves to a negative side. If it's on a negative axis, it moves to a positive side, just because we are rotating it by 180 degrees. So z, let us consider z new is on a positive one, so the result will be a negative result for the z. And same with the yz plane, where y and z are constant and x is changes its value, and in an xz plane x and z remain the same and the y change then so that's CD reflection. And now we have discussing about the shearing. What does the shearing mean? Shearing is ideal technique to change the shape of an existing object in 3 plane. The object size can be changed along x direction, y direction, as well as z direction too. So shearing can be performed in 3 dimensions, which are shearing in x-axis, shearing in y-axis, and shearing in z-axis. So shearing next moving uh, so at the point of the toe has been sheared in 3 plane. So initial coordinates be x all, y all, and z all, and shearing parameter for toe x sh of x, and y direction is shy, and z direction is sh. So new coordinate will be x new, y new, and z new. So shearing in x-axis, so x-axis doesn't change, so x new remains the same. It's just x old goes to for the x new, and y all plus the parameter towards y direction which SSY is added into multiplying with x old gives the y new, and for the z new z old plus sh shading parameter towards z direction into x old gives the y z old added to it gives the z new value, and in y axis the y old goes to the y new, and same axis with the x new that x old plus sh for the x being it will be shading sh of x and multiplying to y old, and for the z new z old and sh of z and y old for the z axis shading is performed z axis, so z new will be z old and y new will be y old into sh of y. Y is the shading of the y axis into z old, the shading absent on z axis, right? So in the same way x new is given to x old plus hx of x into z. And moving to the final topics, it's transformation between 3D coordinate systems, and consider Cartesian reference frames where we can assume that XYZ are system. So XYZ is a system, XY dash is a system which is defined with respect to XYZ system. To transfer the XYZ coordinate system to XYZ system, we first repeat translation that brings XYZ coordinate origin to the position of the XYZ origin. So perform the translation, it becomes the origin place, and which follows a sequence of rotation which allows it to assign coordinate to the. So also we can use the unit vectors to form the coordinate axis rotation matrix, and they are as x1 x2 x3 and y1 y2 y3 and z1 z2 z3, and the 4 dimensional vector will. And the final topic is orthogonal vectors, and we say that two vectors are orthogonal if they are perpendicular to each other and the dot product of the two vectors is 0. So if the two vectors here u and v and the dot product is 0 and they are perpendicular to each other, so these u and v are orthogonal vectors, and all these three vectors are mutually perpendicular to each other. If three vectors constitute a coordinate system, cross product of first and second row corresponds to third row following the right hand rule, the orthogonal matrix. And here if you see the first row and second row cross product gives us the third row, and v1 v2 v3 and they're perpendicular to each other, and so they are orthogonal vectors. So thank you guys, thanks for being here, and this is Team Benjamin signing out.